Welcome students, welcome to the next session of Strength of Materials 1. So in the previous classes we have started our discussions on thin cylinders and thick cylindrical shells stresses. Today we have started simply, firstly we learned about tensile stresses, shear stresses, compressive stresses, and then now I am applying those stress, strain and all the remaining concepts to the cylindrical members. Okay, till now we observed for a normal beam type member. Now I am observing for the curvilinear type member, right? So in that first part is regarding the thin cylinders. Okay, in that the different types of stresses will be generated. Why the thin cylinders are being used for us? Firstly, simply we are going into a small revision of the concept. Okay, so the thin cylinders. So in this thin cylinders, what I am observing? So when I am using a container which is having circular in cross section and it is containing some fluids which are offering pressure on the structure, right? So when I am using a container for storing some fluid which is either a liquid or a gas, so this cylinder is having circular cross section. Such a type of cylindrical shells, when its internal diameter by 20, the ratio of internal diameter by 20, and when you observe the thickness of the container, when this thickness is very lesser than this d by 20, so the ratio of internal diameter divided by 20, that ratio value is having higher quantity than the thickness of the material of the sheet which we are preparing the cylinder. Okay, such a type of cylinders we call them as thin cylinders. If the thickness is more than 20th of the internal diameter, if the thickness is more than the 1/20th of internal diameter of the cylindrical shell, then those will be considered in the thick cylinders. Okay, so this is the main classification for the thin and thick. So d by 20, if the thickness is lesser than d by 20, d is internal diameter, please remember, and if the thickness of the member is more than d by 20, that is internal diameter by 20, that value, then this condition is thin cylinders, this condition is thick cylinders. Okay, now in thin cylinders, what are the stresses you observe? In generally, every cylindrical container may have circumferential, longitudinal, and radial pressure. Circumferential stress, longitudinal stress, and radial pressure. These are the things any cylindrical container which is having some pressurized fluid inside will have. Okay, firstly I am going into a basic thing which is circumferential stress. So, in case of circumferential stress, what do you mean by the circumferential stress? So, when along the circumference, when the stress is coming, that is called as circumferential stress. So, that is sigma c, or this circumferential stress has another name, that is hoop stress. Okay, sigma c or sigma h, both are same. And then the longitudinal stress. In the name itself, it is giving longitudinal, so sigma L I am indicating. This both circumferential and longitudinal stresses are tensile in nature. They are trying to increase the diameter. They are trying to increase the length. So here the cross section of the pipe is trying to be increased. This is the resistance and this is the fluid force on the left section. So in this way, it is trying to increase the length. Here a resistance will be offered along the circumference tangent to the circumference, and the fluid pressure will be applied upwards. Okay, this condition also will cause increase in diameter. So this causes increase in the diameter of the member. Okay, so this is the way it is happening, and this is for the longitudinal stress. And the last concept we said is radial pressure. Okay, so a radial pressure is, so with the name I am indicating PR, radial pressure, which is the third phenomena or the third type of stress which may occur in generally containers or the cylinders. Okay, the first thing is radial pressure. So in case of radial pressure, what we have said, when any fluid is inside, it is offering some bursting force, so some pressure is offered by the fluid onto the cylinder. That pressure, when it is coming in the radial direction, that pressure we call it as radial pressure. Okay, so when you observe a cylinder, radially the pressure will come onto the walls, on the inside walls of the cylinder. So the stress at this point is the quantity of the fluid pressure offered. So the stress at this interior, okay, internal diameter or the inside of the particular shell is particular radial pressure or the pressure offered by the fluid. And on the outside of the container, that pressure is equal to 0. Why it is 0? When it is kept in the atmosphere, no other force is making the body too pressurized. If some other pressurized fluid is also there, in that this container was placed. So outside is also some pressure is there, inside due to fluid also some pressure is there. If the container is placed in the atmosphere directly, the outside will have 0 pressure and the inside fluid will offer some pressure onto the internal container, and that internal walls of the container will have the corresponding radial pressure is equal to pressure offered by the fluid. As this is trying to do like this nature, so this radial pressure is offering some compressive, okay, it is trying to reduce the thickness like nature, okay, so this is compressive in nature. And these two are tensile in nature, as they are trying to increase the dimension. One is trying to increase the diameter, another one is trying to increase the length. So these two we call it as tensile nature stresses, and this one we call it as compressive nature stress. Okay, so this is the way we are thinking or giving the basic main stresses. Now after the classification of thin cylinders and thick cylinders, now I am observing what are the stresses may arise in thin cylinders. So in case of thin cylinders, I am removing one phenomena which is radial pressure, because in case of thin cylinders, I am neglecting this radial pressure because its value is very less compared to the hoop stress and circumferential stress. So what are the priority stresses? Those only I am using. These two are the priority stresses, and I am neglecting this radial pressure in case of the thin cylindrical shells. Okay. So now as the stress is being produced, the corresponding strain also will be produced, right? So now I will give the corresponding formulas for the stress and strain. Sigma H. So you should have to remember the formula. Sigma H is equal to PD divided by 2T, and sigma L is equal to PD divided by 4T, and P is equal to pressure offered by the fluid and D is equal to internal dia of the fluid and T is thickness of the thin cylindrical shell. Right? So this is hoop stress and longitudinal stress. As the stress we know, now I can say the corresponding strain also. And for giving the strain, we are using Hooke's law and Poisson's law at a time. Okay. So not only Hooke's law, at a time Poisson's law also will be used when I am writing circumferential strain, which is equal to sigma c by epsilon, Young's modulus minus mu times sigma L by Young's modulus. As two mutually perpendicular stresses are acting at a time on the cylinder, so strain corresponding to one directional stress and strain corresponding to the stress in another direction. That's why minus mu times sigma L by E. And from this you can generate PD by 2TE minus mu times PD by 4TE. Okay, so in this way, when you separate PD by 4TE, 2 minus mu will come. So this is the generation of the circumferential strain. And then longitudinal strain EL is equal to, first term is from that longitudinal strain corresponding to the stress in the longitudinal direction, and then minus mu times sigma C by E. Why it is sigma C or sigma H, both you can use. Circumferential strain or circumferential stress or hoop stress. Okay, sigma C, sigma H, same. Sigma L is different. C or H, circumferential or hoop stress. Okay, so this one again PD by 4TE minus mu times PD by 2TE, and which is giving us, so PD by 4TE 1 minus 2 mu. So this is the small arrangement, and I have took the same term PD by 4TE common, 2 minus mu and 1 minus 2 mu. So these are the hoop stress and longitudinal stress, hoop strain and longitudinal strain. When these things are happening, the corresponding strain is causing, so circumferential strain is causing change in the diameter. That's why I can equate delta D by D is equal to circumferential strain. So with the rearrangement, and I can write from this condition delta D, answer you can develop. Okay, from this arrangement delta D by D, and this is equal to epsilon C, and I can give the delta D, change in the diameter formula. And here also this is a strain in the longitudinal direction, nothing but change in the length. So which is equal to delta L by L, which is equal to delta D by D. So after knowing the stresses from the given data, once the stresses known, the corresponding strains you can calculate. Once the strains known, the corresponding change in diameter, corresponding change in length. These three terms you can calculate. And then if they are asking for the volumetric strain in the cylinder, what is the thing you should have to do? The corresponding strain in the cylinder is equal to delta V by V, which is equal to delta L by L plus 2 times delta D by D. Okay, as you already know these ratios, simply substituting those two terms. Okay, pi d square L, right? So pi d square by 4 into L. From that I have got the volumetric strain, as we have already calculated volumetric strain from the basic strain conditions. Okay, so in this way we can calculate the basic strain formula. Okay, so using this basic concept, now I am dealing a problem so that you can get the enough clarity for the substitutions. See here, a thin cylindrical shell is 3 meter long, and so it is having a length of 3 meters, and it is having an internal diameter of 1 meter. D is equal to 1 meter. Everything is in meters. Later if needed we will have to substitute in millimeters. Okay, and then it is being subjected to an internal pressure of 1.2 megapascals. Okay, now if the thickness of the sheet is 12 mm, so everything they are giving 12 mm thickness. Find the circumferential stress, longitudinal stress, change in the diameter, change in the length and volume. Okay, change in diameter, length and volume, and the corresponding stresses. So firstly, what they have given, from that what you should have to use the formula, and finally what you can reach. So till now what are the formulas we have discussed, that only we have came to the point. Okay, first thing is converting everything into millimeters so that you can use the corresponding answers, and they have given the corresponding Young's modulus and Poisson's ratio. Why these things are needed? For getting strains. In the strain equation, Young's modulus and Poisson's ratio are there, right? So firstly we should have to calculate the stresses, and then we will calculate the strains, and then we will came into change in length and change in diameter, and finally change in volume we will calculate. Okay. So the first step, simply I am writing everything into my millimeter form. Okay. So length is L is equal to 3000 millimeters and D is equal to 1000 millimeters and P, pressure, is equal to 1.2 10 power of 6 Newton per meter square as 1.2 into Newton per mm square only. Mega pascals is there, Newton per meter square, and converting 10 power of 6 I have got, and cancellation I have got 1.2 Newton per mm square, and they have given the thickness is equal to 12 mm, and also they have given Young's modulus 200 into 10 power of 9 Newton per meter square, and I have got 2 into 10 power of 5 Newton per mm square, because meter square has gave me 10 power of 6, so after cancellation 2 into 10 power of 5 I have finally left, and they have given us the Poisson's ratio mu is equal to 0.3. So if needed we should have to write all the given data. So better converting all the terms and keeping what the thing you needed, better you should have to write the given data, then go into the solution. Okay. So this is the data needed for me. I have generated all the data in my own terms to substitute. First thing is calculation of circumferential stress or the tube stress. So there is sigma C or sigma H. This sigma C or sigma H is having a formula P D divided by 2T. If you forgot the formula, you should have to use the basic condition, resisting force and the bursting force. There also you can calculate. Okay. So here I have got PD by 2T as the circumferential stress or the hoop stress. So just now I have got P answer. D I know. 2 as it is a constant. T I know. Okay. Sorry, 12 millimeter only they have given. Sorry ma'am. Okay. 12 millimeter. Now I am substituting everything. P 1.2 Newton per mm square as it is 1.2. D 1000 millimeter divided by 2 into 12. So this is the condition for the PD by 2T calculation. And then sigma L is equal to, as I have got this answer as equal to, cancellation of this term has gave me 10 and this cancellation, and 1000 has given me 50 Newton per mm square. Okay. Now I know sigma L is equal to PD by 40. Either again you can substitute the everything P D divided by 4 into T, or you can write sigma L, the longitudinal stress, is equal to sigma C by 2. So in any way I can write the same thing, PD by 40 which is equal to sigma C by 2 or sigma H by 2. So 50 by 2 which is 25 Newton per mm square. So this is the stress occurred in the longitudinal direction. So stress occurred in the circumferential, that is circumferential stress, and stress in the longitudinal, that is longitudinal stress. Now I am going into the strains calculation. Why I need to go into strains calculation? Once I calculate the strain, from that change in diameter, change in length can be evaluated. Okay. First thing is circumferential strain, which is epsilon C. So this epsilon C is equal to, so we have already generated the formula. Otherwise, you can simply write epsilon C is equal to sigma C by capital E minus mu times sigma L by capital E. From here also direct substitution you can go, or from this PD by 2T substitution, PD by 4T substitution, and taking out the commons, that way PD by 4TE into 2 minus mu. So PD by 4TE into 2 minus mu, with that substitution I have got this formula. No need to remember separately. You should have to remember is this thing. From the Hooke's law theorem, later we came into lateral strain, longitudinal strain concept. Then two mutually perpendicular stresses are applied on a beam at a time. So in that condition the body is having this strength. Okay, so this condition I am substituting, and substituting this 50 2 into 10 power of 5 minus 0.3 25 2 into 10 power of 5. So with this arrangement, after calculation of P into D divided by 4 into D into 2 minus mu divided by capital E. Okay, 200 into 10 cube or 2 into 10 power 5. Anyway you can write. So the final substitution has gave me some answer. That is a circumferential strain. Please don't keep the units. Okay, that is strain answer I have got as 2.125 into 10 power of minus 4. Okay, 2.125 into 10 power of minus 4. As I have said, the fluid is pressurizing, trying to increase the cylindrical diameter. That's why that increase I have shown. Okay, now change in the diameter. How can I say? The change in the diameter delta D is equal to epsilon C into D. Circumferential stress strain into that corresponding original diameter multiplication has given change in the diameter. So as is keeping and multiplication of the internal diameter of the container, and multiplication has given 0.2125 millimeter, which is the increase. Originally the container is 1000 millimeter in diameter, but due to the fluid pressure it has increased. How much diameter increased overall? So as initial diameter is D, and when you observe the final diameter, final minus initial, that increase in the diameter is 0.2125 millimeters. It is not even 1 millimeter. 0.2125 millimeters of the diameter is increased due to the pressure of the fluid. Now I am going for the change in the length. Okay. Sorry. Sorry, maybe I forgot to keep the change in the length. So like the same, you can evaluate change in length also, which is EL sigma L divided by E minus mu times sigma C divided by E 25 divided by 2 into 10 power 5 minus 0.3 into 50 by 2 into 10 power 5, which is equal to some quantity and which is equal to delta L by L. As the strain is longitudinal direction, that's why strain in the longitudinal direction will be equated, and from this multiplying L to that side, I can evaluate what is the change in the length of the particular cylinder. Okay, so this is the way for the longitudinal strain. Okay, the next thing is volumetric strain. So the volumetric strain is equal to dV by V. Okay, this dV by V, how can you say? Just now only we have mentioned further also, as this dV by V is equal to dV by V, or you can indicate delta V by V. Anything is the same, just change in volume by original volume, like is the meaning, right? Here, strain in L by, either I can write change in the delta L by L plus 2 times delta D by D. So delta L by L is my strain in the longitudinal direction, and 2 times strain in the circumferential direction. So substituting EL and EC, which we have generated here and the previous step. So see here, from this step I have got PD by 4TE into 2 minus mu, and for L I have got PD by 4T into 1 minus 2 mu. So using these two formulas and substituting in the volumetric strain formula, I have got a final rearrangement as PD by 4TE into 5 minus 4 mu. So PD by 40 into 5 minus 4 mu we have got, and that I am substituting here, and in the substitution as it is P, the pressure 1.2 Newton per mm square, and internal diameter 1000 millimeters, 4, and T thickness is 12 mm, and small is 200 into 10 cube or 2 into 10 power 5, anyway you can write, and 5 minus 4 into 0.3. Okay, so this is the way we are substituting, and the volumetric strain, okay, the volumetric strain I have got as 4.75 into 10 power minus 4. But in the problem what they have asked, what is the change in the volume? Okay, So this is volumetric strain. That's why after multiplying it with the original volume, I can get. So the change in volume dV is equal to strain into original volume, keeping as it is the strain, and volume of the cylinder. Volume of the cylinder is equal to pi d power 4 by, pi d power 4 by 4 into thickness of the length of the cylinder. So when I am calculating this, B L so area pi d power 4 by 4 into length. So cross section area into length will give the volume, right? PDQ will select that, right? So area into length, and pi into what is the internal diameter of the cylinder. Everywhere I am using internal diameter only. I am not at all thinking about the external, because compared to internal, as it is internal is 1000 millimeters and the thickness is 12 mm only. So like that external diameter and that concept we will not recognize. Okay, only internal diameter. From that only I am calculating the volume, because the volume of the fluid only causing the body to expand, right? So pi by 4 into 1000 square, d diameter square, and length of the cylinder is 3 meters. We have got 3000 millimeters, and substituting with rearrangement, and I have got millimeters, because everything is in millimeters. That's why you have got this millimeter cube.